just run anything on my laptop. It's very
Okay. Okay, we'll pick up where we left off last week. So today we're going to finish up hydraulic components, and then just remember, since we'll be finishing the unit, I'll be posting a quiz that covers hydraulics. That will be due on Wednesday at 11:59 p.m. Okay. And then I'm also going to hand out the schematic assignment that goes along with hydraulics. And that I will make due on Monday at 11:59. So you have the full week to finish that up. So when we left off, we'd finished up valves, and now we're on to actuators. And so actuators, the first way we're going to classify them is there's generally two types of motion that they can produce. So the first is linear actuators, and these are going to convert that fluid pressure, which is a form of energy, or convert it from pressure to linear motion, to kinetic motion. The other type is rotary actuators, and these are going to convert, these are going to turn fluid pressure into rotary or rotational or spinning motion. Rotary actuators then have two subtypes. The first is called rack and pinion, and those are kind of a combination of a linear actuator creating a rotational motion, and the key there is there's a limit to how far they can rotate. They have a set number of rotations one way, and then they can be reversed to go the other way, but they can't produce unlimited rotary motion. The second type is your hydraulic motors, and these, just like any other motor that you're probably familiar with, any other rotary motor, these can spin indefinitely in a given direction. And so we'll look at those. So linear actuators look something like this. Here's the large one. Okay, rather large one. This was for a cargo door. And then when we're looking at linear actuators, these can be broken down into two types based on how the hydraulic fluid, or what directions the hydraulic fluid moves the actuator. And so in the case of a single acting actuator, we're going to use hydraulic pressure to move the actuator in one direction. Now, it doesn't mean it can't move in the second. Obviously, the point of a linear actuator is to be able to go back and forth. And so that motion in a second direction is going to occur using some other force besides the hydraulics. So it could be a spring built into the actuator itself. So you use hydraulic pressure to push it one way, and when you release hydraulic pressure, the spring pushes it back the other way. Extend, retract, or however you want to call it. The others can be things like gravity, right? So if you're talking about in some cases, not so much on transport aircraft, but some aircraft, for gear extension, right? You could use pressure to raise the gear and then just gravity to lower the gear. More of an emergency extension type situation. Same thing with like doors or air stairs. So like the 727 we had air stairs that dropped out of the tail. They were hydraulically retracted. They got pulled up hydraulically, but the extension on it was mainly performed by gravity. Now, it did have a certain amount of hydraulic action that occurred to help lock it down, but the actual motion, most of the action that was required to push the stairs down, was simply gravity causing it to free fall. And so in that instance, if hydraulics were off, you could still open the stairs, for instance. Or like a cargo door, a big cargo door, the ones that open up on the side of the plane, if hydraulics are off, most of them are able to close just by releasing hydraulic pressure. And so some other non-hydraulic forces you return. In the case of a double-acting actuator, you have the ability to use hydraulic pressure to move both directions. And this actually is, even though it's a door actuator, it is a double-acting. Like I said, it can be closed without hydraulics, but it would be closed. Normal operation would be using hydraulics because that can be used to help force it shut to get it to lock. But in a double-acting actuator, then we further break it down, and that is whether an actuator is what's called balanced or unbalanced. And that refers to the amount of force that's available. And so in an unbalanced actuator, the way we calculate force, the way we understand force in a hydraulic system is, remember, our hydraulic system runs at a certain pressure, right? And pressure is given in, write it a different way. Pressure is given in pounds per typically square inch, right? PSI, pounds per inch squared. And so what we can figure out is if we know the surface area that fluid is pushing against, the surface area would be given in square inches. So this is the pressure here times a surface area, right, which is given in inches squared, right? That gives us our force. These cancel out, inches squared cancel out, and that gives us just a straight up force in pounds. Okay? So if you have an actuator with two different size surface areas, you're going to have a different force pushing in each direction. Okay? And so that's where the term balanced versus unbalanced. In a balanced actuator, we have equal surface, and I'll show you here some diagrams, some cutaways that show how each of these are done. So this top left here is a single acting actuator. You can see that, and I'm going to use the mouse for the recording. You can see that we have a kind of a piston in the middle with a seal going to the output shaft. Fluid is able to come in the left side, and then here we have a return spring that would push it back to the left on the right side of it. And so that's single acting. Below that is a double acting, so now we can port fluid to either side. Now one thing I don't like here, and I think it was a typo, is there should be a seal across the middle right here. Okay, so there should be a line there. They misplaced it, I guess. But there would be a seal across the center of that, and fluid can be ported in the left or the right side. Now, because of that though, in the case of any of these, if we want to move the actuator, say if we put fluid in the left side, right, on the top one, it's going to compress the spring. On the bottom one, the double acting one, we're going to have to allow the fluid that's in this case, coming from fluid port 2, we have to allow that to flow out, right, for that to move. And that'll be ported to the return side of the system. So pressure would be ported to the left, fluid port 1, and then it would be ported to the return from port 2. If we want the spring on the single acting to be able to move that actuator back, we have to release that fluid pressure on the left for the top left actuator. And so in that case, the fluid here would be ported back to the return, right? So we're either going to have pressure go in or return to allow it to flow out. So this bottom one here is a double acting, but it's unbalanced. And the reason it's unbalanced is on the left side, right, we've got the fluid is pushing against the entire surface area here. So, our fluid is able to push against the entire surface. And it's really hard for me to do this looking at a screen, but we can go across the whole surface. So great arrows there. Okay. And then, but on the right side, you can see when we retract that actuator, in this case now, only fluid is only going to push on essentially a ring or a donut that's around the outside of the output shaft here, right? So there's less surface area that fluid can push against. And so you'll be able to get more force extending this actuator than you will retracting the actuator. So that's what that term unbalanced. So something like this, where might we see an unbalanced actuator? What do you think is a common setup? What kind of things would use an unbalanced actuator? Just a hint. No? What needs less force in one direction than the other? Landing gear, right? You need probably more force to put it up, and then gravity's helping you when you bring it down. Most of the time, again, landing gear, that little bit of force, all it's doing is pushing it into the lock position once gravity's gotten it most of the way down. And even that often is taken care of because you have air. You have slipstream you can use to lock the gear down. Okay? Or the cargo door was the other example. So here's that cargo door actuator, right? Fluid ported in the bottom of this actuator. I don't know if I draw on here. Does this show up on yours? Hey, it does. That's much easier. So when fluid's ported in the bottom, right, it's going to have a lot larger surface area. than the fluid that is ported into the top up here. Okay. And here we have two different surface areas. Now on the top right, we have a double acting balanced actuator. So you can see in this case there are two shafts on it. It's showing two shafts that have the ability to connect, to connect something on each side. But because the two shafts are the same diameter, they're going to reduce the amount of surface area that fluid is pushing on by the same amount. And so for this balanced actuator on the top right, we're going to have equal force for going extend or retract. Now, this is kind of an oddball, this double acting actuator. Most of the time, they don't have, you can see it's got a connection point at both ends. Most of the time, they don't have a connection point at both ends. They simply have they have what's called a dummy shaft. And when you have a dummy shaft, it looks something like, then I could change my pen size. I guess not. Well, when you have a dummy shaft, whoops. It essentially ends, my very tiny pen. You don't have a connection point on both sides. So it's just got a shaft that sticks out the opposite side, kind of like that. And so it'll be balanced, but it'll only connect on one end. Okay. And that end, again, that's your dummy shaft is the name for it. Okay. Actuators also can operate in two manners. Linear actuators can operate in two manners of whether they are what's called a full travel actuator or a partial travel, also known as a servo, a feedback, or a proportional actuator. You can see those three terms are pretty interchangeable. And what the difference is, the full travel actuators, these are ones that if you're porting fluid to them, they are going to go full extend or full retract, as long as the valve is open, okay? And things like your landing gear, right? You usually don't put the landing gear up halfway, right? Doors usually aren't halfway open or halfway closed. Some of your secondary flight controls are going to use full travel actuators. The example for that, when we get into, you'll see it more, but the biggest example of that is something called a ground spoiler. And that is when the plane touches down. If you've ever flown and looked out at the wing when the plane touches down, as soon as the wheels touch the ground, there are big panels on top of the wings that pop up and they spoil lift. They basically push the plane down onto the ground. Ones that strictly serve as ground spoilers are going to be full travel actuators because they're only ever going to be fully up and fully down. Now, most transport aircraft, that's not the only thing the spoilers do. They're often used as flight spoilers. They're often used as speed brakes. And so they probably do have the ability to vary. But a lot of transport aircraft do have dedicated ground spoilers that are only activated on touchdown. And so they'll put a simpler full travel actuator in rather than putting a servo actuator in. So servo actuators have to have they still are pretty much the same type of actuator. The actual actuator itself isn't much different. But they include an integral valve, servo valve, and mechanical feedback system. Okay? And that is, things like primary flight controls where if we move the yoke, say we want to roll the airplane, we move the ailerons just a little bit, right? When we tip the ailerons just a little bit, that operates a hydraulic valve. We don't want it to send the ailerons to full deflection and put the plane into a roll, into an actual inverted roll, right? We want to just, the crew's probably just lining it up for the runway or something, or making a slight bank in order to change course. Same thing with the rudder or the elevators, right? We just want them to move a little bit if we move the yoke a little bit. Okay. The rudder, you just want it to move a little bit. In fact, rudder, if you go full travel at full speed, you're going to rip the tail of the airplane off. And so you definitely don't want that to happen. So primary flight controls, many of your secondary flight controls, like the flight spoilers and the speed brakes, those are going to use these servo and feedback actuators. So I'm going to go ahead and play the video here. For those that are joining at home, you can watch the video from the links that are on e-learning.
You have no idea how
Our other type of actuators then we have were the rotary actuators. And so here is a kind of a taken apart rack and pinion. And this is going to combine a linear rack with a pinion gear. And it can operate a couple different ways. So what's shown here is a hydraulic rack and pinion actuator that uses a linear actuator to move the rack back and forth. That's the part that's circled there. Let me get my pen. Oops. So we have that circled, this linear actuator here. So fluid can be ported to either side of the piston that's on the end of it, the piston right here. And that's going to push that linearly, we'll say left to right in this diagram. And as it rotates, you can see it has a rack on it. That's this toothed section on the left. And as that tooth section moves left to right, it interfaces with the pinion gear down here. And so when it moves from left to right, it's going to turn that pinion gear, if it moves from right to left, if it's getting pushed right to left, that is going to cause that pinion gear to turn counterclockwise. So I'll erase my markings. So if the rack is pushed to the left, that's going to cause my pinion gear in this setup to rotate this direction. Okay. And consequently, if we reverse the flow of fluid and we push our rack out to the right, that is going to turn the pinion gear the other direction. Okay? Because in this case, it shows the rack interfacing at the top of the gear. Okay, that could be reversed if it was flipped over. Okay. Now the other side of this, below here I have hydraulic motors, and we've seen kind of a hydraulic motor in action already when we were talking about power transfer units earlier on. Back when we did pumps, I talked about how a power transfer unit is a combination essentially of a hydraulic motor and a hydraulic pump. And a hydraulic motor, most hydraulic motors that we're going to see on transport aircraft work like a pump in reverse. So they are piston based. They look like very similar to a piston pump, but instead of mechanically rotating the input shaft, and that creates pressure, the pressure pushing on the pistons is going to cause it to rotate. And they do not have the variable inclination that the pumps have, that your constant pressure variable flow. The swash plate is at a fixed angle because they're designed to operate at a certain speed. There may be some variable speed ones out there, so you can use a swash plate to adjust the speed, but for the most part, they're a fixed swash plate in order to run at a certain speed. And so that's going to be the most common. They work like that. You do have other ones that are like gear types and vane type pumps, which you studied in light aircraft systems. And the same thing, those you run pressure into them, a gear type. That hydraulic pressure forces around the outsides of the gear, it causes it to turn. The vane type, center part with veins sticking out, the fluid pushes around, moves the veins around, causes it to rotate. But again, most of ours are going to be the axial piston type that we talked about earlier because they can handle and they can operate at higher pressures. Now there is another type of rack and pinion actuator where we use rather than in the case of what I'm showing here where we use hydraulic pressure to push a linear actuator back and forth, you can also set it up where that pinion gear is rotated by a little hydraulic motor. And so you can spin the pinion gear one way to push an output shaft one direction, and you can rotate or spin the pinion gear the opposite direction to push the output shaft the other way. So you can use, in that case, pressure to create rotary motion, which then gets converted into linear motion. Okay. So rack and pinion motors can actually work, or actuators can actually work both ways. They can give either a rotary output or a linear output, depending on the configuration, where you're putting the fluid in and what it's operating. Now, on that note, you can see with that there's a limit to how far, a rack and pinion type linear or rack and pinion actuator, it's going to be able to only travel a certain amount one direction before it has to be reversed and travel the other direction, kind of like another, your linear actuators. The hydraulic motors, those are the ones that allow for unlimited rotational motion one direction or the other. Okay. In our systems, we also need to make sure that our fluid remains clean. So with all of these actuators, I'm going to kind of go back to this real quick. With all of our actuators, they are designed to leak a little bit. Okay? Just know that all hydraulic, and even rotary ones not so much, but all linear hydraulic actuators are going to have a certain amount of fluid that is able to escape from the actuator. The reason for that is we have these seals. The seals that are on the actuator piston, right? They're right next to fluid. The inside of the actuator there has fluid on the walls of it, and that allows that seal to move back and forth. But we have to be able to lubricate that interface between the steel components and the rubber seals. And so on something like the double acting actuators here, you can see that we have most of the time it's a steel shaft running through a rubber seal. And so the design of these is such that fluid is designed to coat, a very, very thin layer of fluid is designed to coat that steel shaft so that it can provide lubrication as it moves through the rubber seal. Okay? What that means is hydraulic fluid does go, when these, say this bottom actuator, when it extends, the double acting unbalanced, when that extends, a small amount of fluid is going to go from inside the actuator to outside. And over time, it will be enough that you may get a drip or two that ends up, on a panel or something. So like most of the aircraft, every aircraft I worked on, commercially, because we didn't repaint them as often, the ailerons and the elevators, if you looked right below where the actuators were, they almost always had some paint missing. And that's because phosphate ester fluids, Skydraw fluids, are really good at stripping paint from aluminum. And so they almost always had some paint missing unless they had just come from paint. It doesn't take long for them to start bubbling away from that little bit of fluid that comes from those actuators. Okay. The other part of that is that fluid that coats the actuator, hydraulic fluid, over time in particular, gets sticky. And so things like dirt and dust and other things like that stick to that. And when that actuator retracts, it's going to pull a small amount of that dirt and dust back into the actuator, into the right side, for instance. And that will end up going back through the return side and it gets into the system. So we need to be able to remove that over time. And that's why we need a filter. Even though they're closed systems, we have to have filters in there, mainly to remove that. The other reason we have filters in there is in case of a component that fails. We don't want one component failing, releasing particulates into the fluid, then getting pumped around to the rest of our system and causing failure of other components. And so we have our filters that remove these different contaminants, okay? And they can be one of two types. They can be cleanable elements or replaceable. Most transport aircraft, they are a replaceable element. And the reason for that is replaceable elements are going to be a finer filter media. Okay? The cleanable filters are a screen, and at the end of the day, you cannot make a screen with holes as small as you can make with a cellulose type element, a paper type element. Now, even though they are cellulose paper elements, they still have a screen over them. So, I believe everyone in here has done the hydraulics lab at this point, right? And everyone in here has seen that filter that we pulled out. That is a replaceable filter, even though it's got the metal screen over it and everything. But remember, these systems are running at 3,000 PSI. You can't just have a paper filter that's designed, like your engine oil filters, right, are paper but they're not reinforced at all, but they're only holding like 30 psi, 50 psi, 80 psi on my boat yesterday. It was running a little high, I think, because it was cold. But 3,000 psi, a paper filter is just going to blow out unless it's supported somehow. And so they're still screened. They still have a lot of metal, but they are a replaceable filter. Ultimately, the filter element is cellulose based. Okay. These filters have integral clog and bypass. They have the ability to bypass if they start to get too clogged, and then they have an indication. And so when you did your filter change, you looked at this filter right here, and here's the top of it, and those two red dots are bypass indicators. And so if the filter becomes too clogged, starts to become too clogged, when you get a filter that's becoming clogged, it gets a pressure differential from the side where the fluid comes in compared to the side where the fluid comes out. And as it gets further and further clogged, there's a point where that pressure differential can get high enough that it can cause one of these impending bypass pins to pop. Okay. Now the reason this one has two is you saw it after it's a post-service bulletin or a post-mod where it just has a single element. This filter bowl cartridge setup originally had two filter elements, and it had a coarse and a fine, and that's why it's got two indicators on it. But that has been replaced by that single element filter that you all saw when you did the lab. So those are the bypass indicators there, what they look like. This is in the set position. Okay, I've tried to pop these. I cannot figure out how to get one to pop without, we're talking about something where you get 3,000 psi. I can't just shoot air into it and get it to pop open or something. So I've tried to get one to pop. I cannot figure out how to get one to pop, so you can see what they look like popped. But essentially they pop up and they stick out about 1/4 of an inch. So when you look at it from the side right now, if you look at it directly from the side, you don't see anything sticking up. If you look at it from the side when it's popped, they stick up about 1/4 of an inch. And so when we did our daily checks on the aircraft, our aircraft, typical transport aircraft operating in an air carrier environment, has to be looked at by maintenance every 3 to 5 days. They would come in for something called a service check. And during a service check, we would look at things like make sure the lights were working, we would check tire pressures, we'd check engine oil levels, and we'd go around to each of the hydraulic filters and we'd make sure that none of the impending bypass pins were popped. They also, in some cases, these bypasses can have a pressure sensor hooked to them or a switch attached to them if you want to be able to give some kind of an indication up in the flight deck. Not all of them have it, most of them actually don't, but if it's one that's critically or particularly important, they may link it to an indication system. These ones right here that are shown do not have any kind of that. They actually do have, if you see that cannon plug above, I misspoke, they do have a pressure indicator right above, but it's not integral with the bypass indicators. It's kind of a separate little switch above. That's what this threaded cannon plug goes to right here. Okay, so this one, it's separate, but it does the same thing. So if we look at, you can see a cutaway here of what these look like. You have a bowl on the left shows normal operation. And on the right, it kind of shows when the filter element gets too clogged, it pushes this poppet and routes pressure to the bottom of this pin, and that causes the bypass indicator to pop up right here. Okay. Now, a lot of times with those, just from a maintenance perspective, probably 9 out of 10 times when one of those popped, it just popped because of a pressure surge in the system. It wasn't because the filter was actually going bad. So the first step in our maintenance manuals, when you found one of these things that was deployed, that was sticking out, the first step, and you reset them, you simply, with the system off, you go up and just push back down on it. It'll latch back in place. And so the procedure, when we found one popped, if it was the first time it was indicating pressure, we would make sure the system's off, we would push it back in, and then it said to turn the system on and operate all the, move a bunch of stuff, right? You didn't necessarily have to put the plane on jacks, retract, extend gear, all that, but they would have you move some stuff just to get some fluid flowing. And then go check it again. Now, if it's an engine filter, if it's a filter coming off the engine pumps, you'd have to go out and run engines and that kind of thing. But essentially, you would pressurize the system, operate the system, and see if it pops again. And then that kind of thing, in an air carrier environment, that gets put on a watch, and you make sure it doesn't happen. If it keeps happening, then obviously there's something wrong. But if it was a one-time thing, it may have just been a pressure surge in the system that had just enough of a kick to get it to pop open. Sometimes there are multiple filters together, okay, like what's shown here. This has got 2 of them on one unit. And filters are located in 3 primary locations in hydraulic systems. So the first is you will find one in the pressure area. So between where after the fluid leaves the pump and before it goes out to the hydraulic system, you're going to have a pressure filter. And that's the name of these. They have a specific name. So the pressure filter is downstream of the pump. This is between the pump outlet and the pressure side of the system. Its main purpose is so that pump chunkies don't go to the system when your pump eventually fails. And one of the highest failure items in a hydraulic system is the pump. Right? That's working the hardest. They do fail on occasionally. And remember, most hydraulic systems, you have at least 2 pumps, an engine-driven, an electrical, or a couple electrical. You don't want to send a bunch of pump chunks out into the system and clog everything else up if one of your pumps goes bad. The next one is the case drain. So coming off of the pumps, right? Remember, you have that fluid that comes off your pumps to go to the heat exchangers to cool the hydraulic fluid. And again, in case your pump fails, you don't want to send pump chunkies out. They put a case drain filter in. These are usually much smaller than the main pressure filter. The pressure filter typically is the largest filter, okay? And the return filter is usually similar size. Case drain filter is usually kind of small, right? It's not a lot of fluid, but it's just that cooling fluid. And then finally return. After the fluid comes back from the system, before it goes into the reservoir, we go through a filter one more time. And that is so that if you have a failure of a component out in the system, it doesn't go back to the reservoir. That's also the one that's primarily tasked with removing that dust and dirt and everything else that makes its way into the system by getting through the seals on the actuators and various components. And so that filter oftentimes is a finer, has a lower micron rating, a finer rating, in order to catch that dust and dirt. Whereas the ones that are downstream of the pump, they don't tend to have as fine of a rating because they're mainly looking for failed metal pieces. Okay? If we look at these in a diagram of a system, here is a single thrust reverser system. This is the number 1 system off the Embraer 175. Lots of lines, right? But this one has a filter. They kind of put a lot of the filters into one module. They got a couple separate filters, but there are some here. Okay. So here we have the pressure filter. You can see it's downstream of the 2 pumps. So our 2 pumps are, here's our engine-driven pump, sending fluid to it. And our AC motor pump, sending fluid to it. And it goes into, in this case, it's a 5 micron filter. 5 micrometer, that's a 5 micron. Before the fluid goes out to the system, you can see from that pressure filter, it goes out to the right. We've got all our different users on the right side of the screen. The case drain right here, you can see comes off of the case drain side of the pump. There's one here. If we look at our AC pump, it also has a case drain filter down here. Those are 15 micron. Again, those are looking more for pump chunks rather than dust and dirt. And those are going to filter that case drain before the fluid goes to the heat exchanger, which is right here. Okay. And then eventually that fluid goes back to the return side. And then finally, our third location, our return filter down here. And you can see that if you follow the fluid coming back, it runs through that filter on its way back to the reservoir. And let me get my pen up. So fluid from our various users. Fluid from our various users comes back this way, comes across here, goes up, goes through our return filter before coming back to the reservoir. Okay. And you can see that one also is a 5 micron. So that, again, this one does have fairly low or fairly fine filters on the pressure side as well. It can be either way, but that return one is always going to be at least, it's going to be, you can see it matches or better than the pressure filters. okay, to catch that dust and dirt that's coming back. And that wraps it up.